Hello everyone, I'm Jin Jiang from Tsinghua University. Today I will be presenting to you our work about long-range ambient LoRa backscatter with parallel decoding. This is a joint work with Zhenqiang Xu, Dr. Fan Dang, and Professor Jiliang Wang. Recent advances in backscatter systems bring low power, low cost, small form factor to wireless communication. However, as a trade-off, backscatter communication is suffering from a short communication range and poor concurrency. For example, if two backscatter tags detect the ambient excitation signal, due to the low power characteristics of backscatter tags, it's hard for them to perform complex multi-layer protocols like CSMA, Zeros and backscatter packets concurrently, which overlap in the air, leading to collisions. Such collisions cause frequent packet loss and waste precious power of tags and spectrum. Even if there is only one tag occupying the wireless channel, as the distance increases, the backscatter signal with weak signal strength usually cannot be decoded correctly when it reaches the gateway. Among past backscatter communication systems, LoRa backscatter is considered a promising technology as it greatly extended the communication distance. There emerges with an extensive collection of LoRa backscatter techniques. However, they still have the following limitations. The first one is dedicated excitation signal. Traditional approaches need a single-time RF source, which incurs additional deployment costs. Also, it's better to use ambient LoRa signal to avoid additional spectrum overhead. The second one is no parallel decoding. Past works only work for a single or very few parallel backscatter packets, and frequent collisions lead to lots of packet losses. In practice, it's essential to decode parallel backscatter packets, especially considering the large communication range of LoRa. The third one is complex backscatter modulation. Complex tag design incurs high power consumption and high hardware costs. For resolving this problem, we propose PP-LoRa, the first ambient LoRa backscatter supporting parallel decoding and long-range communication simultaneously. PP-LoRa is compatible with any ambient LoRa signals and works for extremely low SNR backscatter signals. And it can also support large-scale LTE applications by decoding hundreds of concurrent backscatter transmissions. Finally, it's simple to deploy as it's fully implemented as a single antenna base station without any extra hardware modification. We implement a prototype of PP-LoRa with hundreds of customized PCB boards and USRP software-defined radio, and evaluate its performance in a real deployed system. First, let me introduce the overview of our system. PP-LoRa takes the ambient LoRa signal sent by commercial LoRa devices as the excitation signal. The main idea of PP-LoRa tag is to shift the LoRa signal with a certain small frequency to encode data in the backscatter signal. The LoRa gateway receives the backscatter signal from multiple PP-LoRa tags along with the original LoRa signal, and then it performs delicate algorithms to concentrate every backscattered energy and cancel the interference between signals. Finally, it decodes multiple backscatter signals as well as the original LoRa signal simultaneously. To further introduce PP-LoRa, we need to understand the physical layer of LoRa. For encoding data bits, we shift the initial frequency of the chirp symbols. For example, to encode 1 bit, we use a base up-chirp to represent 1 and use a shifted up-chirp to represent 0. At the receiver, each encoded chirp is multiplied with a base down-chirp, resulting in a single tone with the encoded initial frequency. Then we apply FFT on the multiplication to transform each symbol to an FFT peak in the frequency domain. The frequency of these peaks represents the encoded data. To encode n bits with a single chirp, we can divide the chirp bandwidth into 2 to the power n different initial frequencies. In PP-LoRa, every tag is allocated a certain frequency. Then each tag uses the allocated frequency to shift ambient LoRa signals and perform OOK modulation on it. As a result, the backscatter signal consists of 2 parts, upper and lower sidebands, as shown in the formula. Take 2 tags as an example. There are 4 cases in total. They both send bit 1 by using each allocated frequency to shift the excitation signal, showing as delta F1 and delta F2. And one sends bit 1, the other sends bit 0. And they both send bit 0. In our system, tag outputs an easy-to-generate low-frequency square wave, which ensures the low hardware complexity and low power consumption. However, to decode this easy-to-generate backscatter signal, we are facing three challenges. First, the energy of backscatter signal is separated in the double sideband. It's difficult to concentrate. Second, we use a low shifting frequency. This reduces the tag hardware complexity for frequency shifting, improves spectrum efficiency, and minimizes its interference to other channels. However, this also brings challenges for canceling the excitation signal. At last, multiple backscatter signals are overlapped in the frequency domain to improve spectrum efficiency. It's hard to cancel inter-tag interference, especially for a large number of tags. To explain why the energy of backscatter signal is difficult to concentrate, consider this example. When excitation signal is a normal chirp whose initial frequency is 0 Hz, by directly applying D-chirp and FFT to the received signal, we can obtain 4 FFT peaks in the frequency domain, 2 for the upper sideband and 2 for the lower sideband. Therefore, the total energy of the received signal is distributed to 4 peaks, which causes SNR loss. However, if we transform the excitation signal to a base up-chirp, whose initial frequency is -BW second, there are only 2 peaks corresponding to the backscatter chirps in the FFT. In such a case, the energy of a single sideband is concentrated to a single peak. Each peak is twice as high as the old one. But in reality, the excitation signal is normal chirps with different starting frequencies rather than base up chirps. So here comes the question, how to transform the received signal to base up chirp. The key observation is the excitation signal is typically stronger than the backscatter signal. We can first decode the excitation signal by tracking the highest peak after FFT. After decoding the excitation signal, we obtain the starting frequency of it. We can also calculate T prime, which corresponds to the position that a chirp reaches its highest frequency. Then we divide the received chirps into 2 parts, the part before T prime and the part after T prime, marked as gray and pink areas. At last, we switch these 2 parts and splice them to form a new signal. This intuitively results in a base up chirp. A typical backscatter signal uses a square wave to shift the frequency of the excitation signal CT, which results in 2 sidebands in the frequency domain, marked as 2 different color terms in this formula. After switching and splicing, those 2 sidebands are transformed into 2 peaks in the frequency domain. To leverage those 2 sidebands, we calculate the absolute value of the FFT result and add up these peaks non-coherently before and after flipping the FFT sequence. In this way, the backscatter energy of the upper and lower sidebands is concentrated to only 1 peak. Now I will introduce how we deal with excitation signal interference. We propose a method to first reconstruct the excitation signal in the time domain and then cancel it from the hybrid signal. To reconstruct the excitation signal, we need to accurately estimate its parameters, including the frequency, amplitude, and initial phase. As you can see, the raw FFT result of the excitation signal can only lead to cross-grained estimation. To get fine-grained parameters, we first perform zero padding on the D-chirp results. After padding, we have multiple sampling points around the main lobe. Then we perform nonlinear fitting on those sampling points to obtain the height and frequency of the main lobe. At last, we reconstruct the excitation signal and cancel it from the hybrid signal. Unlike the interference coming from the excitation signal, it's difficult to cancel the inter-tag interference, because the power of the backscatter signal is typically several orders of magnitude weaker than the excitation signal, making it difficult to obtain the parameters. So we first add 9 empty FFT bins between 2 allocated bins to lower the side lobes. Then we use a window function, which consists of two hiding windows with different scaling factor. A hiding window smoothly reduces the amplitude of the signal towards zero from the center to two edges. Therefore, it decreases the sharp phase discontinuity and suppresses the height of the side lobe and its interference to adjacent FFT peak. Alright, so now let's see how PP LoRa works in practice. We implement PP LoRa tag using a customized PCB board with low power components, and we use a commercial LoRa node equipped with a SAM-tag chipset. The gateway is a USRP software-defined radio. By default, the bandwidth of the excitation signal is 500 kHz. The transmitting power is 20 dBm. First, we compare PP LoRa with two ambient LoRa backscatter systems, P-LoRa and Aloba. To fully evaluate the performance, we implement a version of PP LoRa without the excitation signal interference cancellation and double sideband energy concentration, named PP LoRa minus. The scenario of this experiment is as shown in the left. We place the gateway in the corner of the room and place the LoRa node outside the room. Then we change the source to tag distance from 1 meter to 30 meters and compare the bit error rate of these four backscatter systems. Aloba stops working when the source to tag distance reaches 15 meters. Because it uses OOK modulation, thus the concentrated signal energy is very limited. P-LoRa concentrates part of the energy of the single sideband backscatter signal, thus achieves a longer communication range. But due to frequency and phase offset in P-LoRa, PP LoRa minus already outperforms P-LoRa when the source-to-tag distance is greater than 20 meters. After excitation signal interference cancellation and double sideband energy concentration, PP LoRa further lowers the BER. So, PP LoRa outperforms other state-of-the-arts, achieves better performance to support backscatter sensing and communication. Next, we test the performance of PP LoRa under long communication distance. In the long tag-to-receiver distance experiment, we put the backscatter tag close to the LoRa node and put the receiver 2.2 km from the LoRa node. Then we measure the BER of the backscatter signal on a different SF. As shown in the figure, when the SF is larger than 9, PP LoRa successfully transmits all the database. In the long tag-to-source distance experiment, we fix the source-to-receiver distance to 200 meters and move the tag between the LoRa node and the gateway. We can see that even when the source-to-tag distance is 100 meters, the backscatter data packets can still be received. In conclusion, PP LoRa achieves kilometer-level communication range and 200 meters coverage. Then we deploy a testbed that contains 101 tags in the office environment. All tags perform OOK modulation on the allocated frequency, and they are randomly placed in those two rooms. As shown in the figure, the overall throughput of PP LoRa increases approximately linearly with the increase of the number of tags. In contrast, without inter-tag interference cancellation, PP LoRa minus shows poor scalability. As you know, when the distance between the tag and the source increases, the power of backscatter signal decreases rapidly. So, we measure the throughput of each tag in room 1. In this figure, redder means higher throughput. With inter-tag interference cancellation, all tags in room 1 demonstrate a high throughput. So, PP LoRa can support 101 parallel transmission. To summary, in this paper, we present PP LoRa, the first ambient LoRa backscatter supporting parallel decoding and long-range communication. We designed a method to concentrate the backscatter signal's energy and another method to cancel excitation signal and inter-tag signal interference. We implemented and evaluated PP LoRa with a customized PCB board and USRP. The results show that PP LoRa can greatly improve the communication range and concurrency of ambient LoRa backscatter. Okay, that's all. Thank you for your listening.